Usually when we talk about a medical diagnosis, there's this underlying expectation of mechanical precision, like you break your arm, the X-ray shows that jagged white line, and the doctor just points at the screen and says, "There it is."
Right, the binary nature of it is comforting. It's broken
Mm-hmm.
or it's intact.
Exactly. But the moment you step into the world of predicting human behavior or financial markets or, I don't know, massive language datasets, that trusty X-ray machine just shatters. The predictive landscape is murky.
Yeah, it really is. We're essentially trying to build mathematical flashlights to see in the dark.
I love that. Welcome back to your deep dive. As you wrap up your machine learning systems course, this is exactly where we are heading today. We're wading into the deep end of supervised learning, connecting all these major predictive models so you can see exactly how they fit together in a real-world system.
And framing this as building mathematical flashlights is a pretty great starting point, because supervised learning is fundamentally about illuminating the mapping between inputs and outputs using labeled examples.
Yeah.
We are largely dealing with two major goals here. First, predicting a continuous sliding scale number, which is regression. Or second, classifying data into distinct categories and calculating the probability of those categories.
So let's start with, the most intuitive flashlight we have. Just drawing a straight line through a scatter plot of data, linear regression.
Yeah, the classic.
Right. You feed it predictors, say, the square footage of a house and the number of bedrooms, and the response variable is the continuous house price.
And the mechanism behind that straight line is ordinary least squares, or OLS. The whole goal is to minimize the residual sum of squares.
Which basically means minimizing the errors, right?
Exactly. If you visualize a line cutting through data points, OLS takes the vertical distance from every single point to the line, squares that distance, and adds them all up.
And squaring the distances is a brilliant mathematical trick.
Oh, it's crucial because it ensures negative and positive errors don't just cancel each other out, and it exponentially penalizes massive outliers. I mean, a point twice as far away creates 4 times the penalty.
That makes total sense for small datasets where OLS can solve the math instantly, but if you have millions of rows, trying to calculate that exact closed-form solution would just melt your servers.
Oh, absolutely. It's computationally impossible at a certain scale.
So this is where gradient descent comes in, right? Most textbooks compare it to walking down a foggy mountain, but I've always thought of it more like tuning a complex analog synthesizer while blindfolded.
I actually prefer the synthesizer analogy. With gradient descent, you are iteratively tweaking the dials, which are the coefficients of your model.
Okay, right.
You turn a dial slightly, calculate if the overall error gets quieter or louder, and then adjust accordingly. You just take step after step in the direction of the steepest decrease in error until you find the sweet spot, the minimum loss.
Let's actually talk about those dials, those coefficients, because I see this trap constantly in student projects.
Oh, I know where you're going with this.
Yeah, if I run a multiple linear regression and the resulting coefficient for bedrooms is 15, someone inevitably reports, every time you add a bedroom, the house value goes up by $15,000.
Yeah, that is a dangerous misinterpretation. The absolute rule of multiple regression coefficients is holding all other variables constant.
Right.
That coefficient means if the square footage, the neighborhood, and the age of the house somehow stay exactly the same, an extra bedroom adds $15,000. But in reality, adding a bedroom almost always increases square footage. You simply cannot view these features in isolation.
And we can't view the model in isolation without checking its underlying assumptions either.
Right, because if the assumptions fail, the line is just lying to you. Linear regression assumes a true linear relationship. It assumes independence of errors, and crucially, it assumes homoscedasticity.
That's a massive word that basically means the variance of your errors stays consistent, right?
Yes, if you plot your errors on a graph and they look like a nice uniform tube, you have homoscedasticity.
But what if it looks like a cone?
Like fanning outward as house prices get higher. That means your model's uncertainty is exploding at the high end. It's highly reliable for cheap houses and completely clueless about mansions. Add in severe multi-collinearity, like, feeding the model both square footage and square meters, which just confuses the math and your reliability vanishes.
So we measure that reliability using metrics like MSE, mean squared error, or RMSE, root mean squared error, maybe MAE. I've always leaned heavily on adjusted R-squared though.
Why is that?
Well, because regular R-squared can be gamed. If you just blindly throw garbage features into a model like, I don't know, the phase of the moon, regular R-squared will sometimes creep up, but adjusted R-squared actively penalizes you for adding useless complexity.
Yeah, that penalty for complexity is vital. Now, everything we just discussed is for predicting a continuous number.
Which, exposes a huge problem if our goal changes. If I want to predict whether that house will sell in 30 days, a probability between 0 and 1, a straight line, is mathematically absurd.
Completely absurd.
A straight line will eventually shoot down to predict a negative 20% chance of selling or up to 150% chance. It breaks the laws of probability.
To fix that, we bring in logistic regression and, despite the name, it is fundamentally a classification tool. We take that straight line of log odds and we bend it.
Bend it how?
We pass it through a sigmoid function, which is a shaped curve. This function grabs any output from negative infinity to positive infinity and mathematically squishes it strictly into a bound between 0 and 1.
Oh no.
You get a clean probability. Then you apply a threshold, say 50%, to assign the final classification.
But since we aren't predicting a continuous line anymore, we can't use ordinary least squares to measure our mistakes, right? Squaring the distances doesn't make sense for binary outcomes.
Exactly. Instead, we use maximum likelihood estimation, optimizing a loss function called binary cross entropy, which is often known as log loss.
Right, log loss.
The mechanism of log loss is fascinating because it's heavily asymmetric. The logarithm curve basically drops off a cliff.
What do you mean?
Well, if your model predicts a 99% chance the house will sell and it sits on the market for a year, the penalty isn't just large, it scales toward infinity. Log loss viciously punishes predictions that are simultaneously highly confident and completely wrong.
Wow. So it forces the model to be deeply honest about its own uncertainty.
Precisely.
And when you evaluate that model in a real system, you have to look beyond raw accuracy. You build a confusion matrix to see your true positives, and false negatives.
Because your evaluation metric has to map directly to the operating context and the asymmetric cost of errors.
Let's play that out for the listeners. If you're predicting fraudulent credit card transactions, missing a fraud case, a false negative costs the bank thousands of dollars, but a false positive just sends an annoying automated text to a customer.
Yeah, so in that scenario, you optimize for recall, ensuring you catch as much fraud as possible, even if you trigger false alarms.
But what if you're an email spam filter?
Then a false positive means burying a crucial work email in the junk folder. That's disastrous. So there, you optimize for precision, ensuring that when you label something as spam, you are incredibly certain.
And you use tools like ROC, AUC, and PRAUC to visualize how well the model separates these classes across every possible threshold.
Exactly.
Okay, I want to challenge a core premise of everything we've talked about so far. Both linear and logistic regression assume smooth, global mathematical relationships across all the data.
That's true.
But what if the data doesn't behave like a smooth curve? What if the reality of the system requires rigid, distinct if-then rules? Or what if we have a dataset with 10,000 sparse features where a single equation would just collapse?
Then we have to abandon the smooth lines and move to decision trees and naive Bayes. Let's tackle trees first. Decision trees are non-parametric.
Meaning they don't assume a predefined mathematical shape.
Right. Instead, they learn highly interpretable hierarchical rules, these recursive splits that slice the data into increasingly pure regions. It works for both classification and regression.
But how does the algorithm actually choose where to cut? Like, if it's looking at loan applicants, how does it know whether to split the data at income over $50,000 versus credit score over 700?
It doesn't guess. The algorithm scans every single feature, tests every possible threshold, and calculates the mathematical impurity reduction for each one.
It wants the resulting subgroups to be as homogeneous as possible.
Exactly. For classification, we measure this disorder using metrics like entropy or Gini impurity. The algorithm chooses the exact split that maximizes information gain.
What about algorithms like CART?
CART, or classification and regression trees, takes this further. It uses binary splits, optimized for categorical classes, or continuous regression tasks via variance reduction.
The danger here, though, is that a tree will just keep splitting and splitting until every single person in the dataset has their own hyper-specific rule. I always picture a deep, unconstrained decision tree, like a student who memorizes the answers to the practice test, but completely fails the real exam.
Because they didn't learn the underlying concepts. That is the textbook definition of overfitting. A fully grown tree has a variance that is just off the charts. It captures every single piece of noise in the training data.
So how do we fix it?
To force the tree to generalize, you must apply pruning techniques. You can constrain the architecture by setting a max depth or requiring a minimum number of samples per leaf.
Or cost complexity pruning.
Yes, which actively penalizes the overall model score for adding too many arbitrary branches.
Why go through all that trouble when we have more advanced models? It basically comes down to governance, doesn't it?
Absolutely. When interpretability and auditability are non-negotiable, like a bank needing to prove exactly why a loan was denied to comply with fair lending laws, decision trees are invaluable.
Because you can literally trace the exact path of logic from the root down to the leaf.
Precisely. You can't do that with a neural net.
Let's pivot to Naïve Bayes, our probabilistic classifier. I have to push back on the name itself. Why naive? It assumes that the presence of every feature is conditionally independent of every other feature. That is blatantly false in the real world. If a spam email has the word Nigerian, the probability of the next word being Prince is astronomically high. They are not independent.
You are entirely correct. The core assumption is fundamentally flawed.
Then why use it?
We accept that flawed assumption because it makes learning computationally tractable, especially for massive, sparse, high-dimensional datasets like text.
Okay, I see.
If you didn't assume independence based on Bayes' theorem, the math requires you to calculate the joint probability of every possible combination of words in a vocabulary. That would crash any computer.
So by assuming independence, you simply multiply the individual word probabilities together.
Yes. And surprisingly, even though the final probability estimates are wildly overconfident, the model still manages to rank the classes correctly.
So it's basically like an incredibly efficient sorting mechanism, but there's a mathematical trap here with zero probabilities. If my model is classifying movie reviews, and it has never seen the word mango in a positive review before, the raw probability is 0. If I multiply a chain of probabilities and hit a 0, the entire equation just collapses to 0.
Which is why Laplace smoothing is mandatory. We artificially add a tiny fractional count to every single feature in the vocabulary. It ensures no probability is ever strictly 0.
That's a clever fix.
It is. Furthermore, multiplying thousands of tiny fractions together will cause a computer to suffer numerical underflow. It basically runs out of decimal places and rounds down to 0 anyway.
Oh, right. So, how is that handled?
To fix that, naive Bayes models transform the math to use log probabilities, allowing us to safely add the values instead of multiplying them.
So, we have these different flavors. Gaussian naive Bayes for continuous data, multinomial for raw text counts, Bernoulli for simple binary indicators.
And don't forget complement Naïve Bayes, which is a brilliant variation designed specifically to handle highly imbalanced datasets.
Exactly, each tailored to the data's structure. But notice a glaring assumption we've been making this entire time. Regression, trees, Naïve Bayes, they all treat every single data point as an isolated, independent event.
Right. Shuffling the rows in your dataset doesn't change a decision trait.
But in reality, what happened yesterday dictates what happens today.
And that transition introduces time series forecasting. The chronological order of time series data completely changes the mathematical landscape.
Because time actually matters.
Hugely. A time series isn't just a list of numbers. It consists of distinct structural components. You have the long-term trend, the repeating short-term seasonality, broader macroeconomic cycles, and, well, the unpredictable residuals.
So, how do we capture a pattern that is inherently moving?
We shift our focus to autocorrelation. This is measuring how much a value is correlated with its own historical shadow. But before modeling, you often have to transform the data to achieve stationarity.
Which means the statistical properties like mean and variance don't drift over time.
Yes, because if the baseline is constantly shifting, the model can't anchor itself.
Got it.
From there, you build models designed for sequences. You can use moving averages to smooth out random shocks, or exponential smoothing to give more weight to recent events. Then you move to autoregressive models, AR, which regress the variable against its own past.
And you combine these into ARIMA models.
Yes, where the I stands for integration, a differencing step to force non-stationary data to behave. Add an S for seasonality, and you have ARIMA, which can also absorb exogenous regressors, like knowing a massive holiday sale is coming up.
Here's the biggest trap I see with time series, though. Graduate students take their data, do a standard 80/20 train test, split at random, and suddenly, their model is reporting 99% accuracy.
Because they just leaked the future into the past.
Right. Predicting a stock price on Wednesday is incredibly easy if your algorithm randomly selected Thursday's closing price as part of its training set.
That's why time-aware validation is strictly required. You must use rolling or expanding window back testing.
How does that work?
You train on a chunk of the past, test only on the immediate unseen forecast horizon, and then roll the window forward. And you have to remember that in production, forecasting models degrade faster than almost anything else.
You mean like performance drift?
Yeah, you are constantly monitoring for concept drift or structural breaks like a sudden global pandemic that instantly render historical seasonality completely irrelevant.
Okay. So time series forces us to respect strict chronological structure. But what happens when we need to build predictive systems on data that lacks inherent mathematical structure altogether? I mean, human language is chaotic, sarcastic, and messy.
Text analysis requires enforcing structure onto that chaos. We treat NLP as a rigorous pipeline, transforming unstructured language into auditable numerical data.
Right.
You start with a corpus of documents, breaking them down into tokens which build your vocabulary or lexicon along with metadata. But before you touch an algorithm, exploratory text analysis is mandatory.
You have to hunt for hidden formatting artifacts, massive biases, or duplication that will just poison the model.
Exactly. And the pre-processing phase is where people accidentally destroy their own data. Let's look at linguistic morphology.
Okay.
You want the system to know that running and ran are the same concept. You could use stemming, which acts like a chainsaw, blindly chopping off word endings. Caring just becomes car, which ruins the context.
Or you can use lemmatization, which is like a scalpel. It references a dictionary to trace words back to their actual root meaning.
The distinction between the chainsaw and the scalpel is perfect. Pre-processing must preserve meaning above all else.
I see this fail constantly with stopwatch removal. People want to save computational space, so they blindly filter out common words like not or never.
Oh, that's a classic mistake.
Right. If your sentiment classifier receives a review of this product is not good, and you strip out the not, you've just inverted the entire reality of the dataset.
That is a fatal domain mismatch error. Negation handling is critical. Once the text is safely cleaned with rejects or whatever, you have to translate it into math. Building a document term matrix using bag of words simply counts word frequencies but completely destroys word order.
Dog bites man and man bites dog become mathematically identical.
Yes. So, to capture context, we use n-grams, binding words together into b-grams or trigrams. But that creates a massive, mostly empty matrix of zeros.
So, how do we manage that curse of dimensionality?
We apply TF-IDF, term frequency inverse document frequency. It mathematically downweights common glue words that appear everywhere and elevates the rare, highly discriminative signals.
So, like, if the word hypertrophy only appears in 3 medical documents out of 10,000, TF-IDF ensures those 3 documents light up like a beacon.
Exactly. From there, you can measure cosine similarity between documents or feed it into supervised sentiment classifiers.
But what if we don't have labels? What if we just have a mountain of text and no idea what's in it?
That unlocks unsupervised topic discovery. Algorithms like latent Dirichlet allocation, or LDA, and non-negative matrix factorization, or NMF.
How does LDA work, simply?
It operates on the probabilistic assumption that documents are just mixtures of underlying topics, and topics are just mixtures of words.
Yeah.
It mathematically unravels the text to cluster-related concepts without any human labeling.
Fascinating. But whether supervised or unsupervised, you must close the loop with rigorous error analysis to catch sarcasm or the negation failures we discussed earlier.
Always.
We have spent this deep dive building an incredible toolkit. Regression for continuous lines, logistic for probabilities, trees for hard rules, Bayes for sparse data, time series for chronological order, and text pipelines for language.
It's a lot.
It is. But every single one of these has severe blind spots. How do we build a system that overcomes the weakness of any individual algorithm?
We build a committee. This is ensemble learning, and it all revolves around navigating the bias-variance trade-off.
So, combining models?
Yes. Ensembles work on the mathematical principle that if you combine diverse weakly correlated models, their individual errors will cancel each other out rather than moving in the same wrong direction.
There are 3 main architectures for this committee. The first is parallel or bagging, bootstrap aggregating.
Right. Bagging focuses heavily on variance reduction. You take a high-variance model, like a deep, unpruned decision tree, and you train dozens of them independently on random subsets of your data.
Because they all see slightly different data, they learn slightly different patterns.
Exactly. Then you aggregate their predictions via a majority vote or average. A random forest is the classic, highly robust example of this.
The second architecture is sequential or boosting.
Where bagging reduces variance, boosting reduces bias. Models are trained sequentially, and each new model is explicitly designed to correct the specific mistakes of the previous one.
Like AdaBoost.
Yes. AdaBoost achieves this by dynamically increasing the mathematical weight of misclassified examples, forcing the next tree to pay closer attention to the hard problems.
What about gradient boosting?
Gradient boosting takes a slightly different route, literally fitting the new model to predict the residual errors left behind by the current ensemble.
The third architecture is hierarchical or stacking, and this introduces a massive potential for cheating.
It really does.
You train a bunch of base models, maybe a random forest, a logistic regression, and a neural network, and then you train a meta-learner model to look at their answers and make the final decision. How does the meta-learner not just overfit and memorize which model was right on the training data?
That requires strict linkage control through an out-of-fold predictions protocol.
Walk me through that.
You split your training data into distinct chunks. The base models are trained on a portion of the data and forced to predict on a held-out chunk they have never seen. The meta-learner is only trained on those blind out-of-fold predictions.
So, It forces the meta learner to learn how much to trust each base model based purely on their unassisted track records. It enforces honest calibration.
Exactly, which brings us to the ultimate reality check for deploying these systems. You simply can't just judge an ensemble by headline accuracy.
Never. Deployment decisions in the real world are exercises in system-level trade-offs. A massive stacked ensemble might give you a 5% boost in accuracy over a simple logistic regression.
But at what cost?
Exactly. If that ensemble requires vast computational cost, introduces system complexity, lacks interpretability, and takes 10 seconds to run inference, you cannot use it for high-frequency trading or real-time fraud detection where latency is measured in milliseconds.
You must also evaluate drift resilience and subgroup fairness to ensure your aggregate accuracy isn't masking discriminatory errors against specific populations.
We have covered massive ground today. To synthesize for everyone listening, supervised learning uses labeled data for prediction and classification. Linear regression models continuous outcomes, while logistic regression estimates class probabilities, punishing confident errors via log loss. Decision trees build interpretable rules, but demand pruning to generalize. Naïve Bayes leverages conditional independence to rapidly process sparse high-dimensional text. Time series requires strict chronological backtesting.
And text analysis demands rigorous pre-processing to preserve meaning before mathematical representation.
And finally, ensemble learning leverages diverse committees to cancel out errors and balance the bias-variance trade-off.
As we close, I want you to consider this underlying dynamic. We are moving into an era dominated by massive black box large language models. You might be tempted to think the traditional ML systems we discussed today are becoming obsolete.
But they're not.
They are not. They are evolving into the vital, auditable governance layer of modern AI.
Because they provide the transparency that deep learning inherently lacks.
Exactly. When a healthcare system needs to prove why a specific diagnostic pathway was recommended in a millisecond, a billion-parameter neural network cannot easily trace its own logic. But a well-calibrated ensemble of pruned decision trees can.
It brings us right back to that X-ray machine we talked about at the beginning. In a landscape of incredibly complex, murky AI, we desperately need models that can give us a clear, visible picture of exactly what is going on inside.
Well said.
Thank you for joining us on this deep dive into your machine learning systems recap. Take these frameworks, examine the mechanisms in your own data, and we'll catch you next time.